Good morning, everybody. Thank you, Chairman, for your introduction. Today, I'm going to give a talk on quantifying modal shape in smart piezoelectric ultrasonic transducer array. Basically, I will give the comparison between my simulation and experimental work. So, basically, this work was conducted during my postdoctoral study at Toyohashi University of Technology. Now I am working as an assistant professor at Bangladesh University of Technology, the second written there. Do I have any pointer here?
It's probably best if you use the pointer of the computer, because you might not be able to point both screens.
Okay. So this is the name of the department where I am working. So in Toyohashi University Technology, we use our on-campus LSI technology, that is a large scale integration. Probably I can see some common faces here from IMEC also. Probably they know it. So, so actually we use that facility for fabricating and characterizing our device. So this is the outline of my talk. First, I will give a brief introduction about the ultrasonic transducer, and especially for single array and also the multiple array, and also how we design the smart piezoelectric pMUTs transducer. That I will give a brief summary on that also. And then also I did the quantification through my simulation work, that I will give you detailed analysis and also the investigation on that. Then how we fabricated the pMUT transducer, we'll show that. And next we'll show the comparison, actually how we correlate the simulation result with the experimental findings. And also we validated through some experimental system our computational and also the quantification through experimental work, modal shape analysis. And finally, I will give some conclusion on that. So let's move on. The trend of ultrasonic transducer. So this slide actually shows the 1D array. So if I put I am actually very poor for moving. Okay, you can see here, just this is the 1D array, and the trend is actually you need if you would like to have the 3D image, so this 1D array actually is not sufficient. That I mentioned here, that for 3D imaging you need the two-dimensional array, and for high resolution also miniaturization, there's problem for the 1D. So you cannot use the piezoelectric bulk ceramics for your high density and high resolution application. So that's why you need to move on the array sensor with crystalline ceramics. That is the thin film. So this is the 2D array that I mentioned here. The present state of art is like if you use the polycrystal, say you have the difficulties in microfabrication, also the interconnection. So how you can overcome this? So that's the way you need to do with thin film piezoelectric material, that you can overcome with those problems. So in this case, you can see here. I'm not sure. Anyway, so you can see in the upper right corner that transducer, actually the 2D array transducer. So in that case, actually you can get a real 3D image that you need for medical application, for example, that I mentioned here. For example, ultrasound endoscopy or something like that. So how we integrated the epitaxial the PGT thin film here. That is In the right side, you can see that the silicon substrate, that is 111, and on top of that, we use the insulating film. That is actually the our great expertise that we have. We use gamma alumina there as an insulating material. On top of that, we use the lower electrode and the functional thin film that I mentioned in the previous 3 slides, that it was like 500 nanometer thickness, and that was used for this ultrasonic transducer. So in the lower bottom, you can see how you can integrate the sensing area, also the signal processing circuit together. So that's the way you can actually integrate a lot of devices together for the 2D array that you need. Otherwise, you cannot integrate information together to get the high resolution one. And also, so okay, so how we design the pMUT array. So in the left side, you can see that 8 by 8 channel pMUT array we designed, and each channel actually consists of 42 elements, and you can see the detail inside that. And right bottom one, it depicts the deposition layer of all thin films. Basically, we also fabricated not only the gamma alumina insulator one, we also fabricated silicon dioxide as a model material, just for comparison, not for our particular application that we did there. So in the in the bottom left picture, actually we use some kind of analytical calculation of the resonance frequency, and that was give you just as a guideline, but you cannot use as a just a tool to design your pMUT transducer, because you cannot get the correct resonance frequency with analytical solution. That's why you need the modeling, advanced modeling that you need. So with finite element simulation, we actually we captured our resonance frequency, that is eigenfrequency, and also the modal shapes of our design pMUT structure before our fabrication. So that actually can save your time, that whether you are doing wrong or right. So you can see the comparison between your underwater and in air environment. You can see that in water is drastically reduced your the resonance frequency that you must need to consider, because for example, if you use for the metal application, then there is a tissue. Actually, tissue is almost nearly identical to water. So that's why you need to consider that one before your fabrication stage. So in finite element simulation, we use MSC Matin method software, finite element coding, but be aware that you cannot use directly that one because there is a water. So then you need to do some coding yourself. That is the thing. So move on the next slide. It shows the mood shapes that we got in air. So you can see that the fundamental mood shape is a 0, 1. So 0 means you don't have any radial diameter on, and only you have the only one direction one. So that is 0, 1. So in 1, 1, you can see that in the second one you can draw a line in the center. That's why 1, and another is the up and down. So that's 1, 1, and so on. So the question is why you are going to do this. The reason is that you need to transfer maximum energy. That is the key factor. So which one you would like to use, whether it is 3, 1 or 0, 1 or 1, 1. So that is the key question. So you also did. I will answer that one. So in underwater, we also did the similar thing. So as I mentioned before, the amplitude of vibration also significantly diminished in case of underwater application, the simulation that we did. So basically, when you have the up and down, for example, 1 and 1, for example, if you consider that, then there is a rarefaction and compression at the same time. So that's you can't transfer maximum energy. But in case of 0, 1, for example, you have always in one direction, whether it's rarefaction in the media or the compression of the media. So that's why you can transfer maximum energy so that your receiver can get that information easily. All right, so how we did fabricated that is depicted here. So I don't know, okay, so probably time will be short, that's why I go quickly. So we deposited gamma alumina, platinum, and also SRO, PGT, and SRO thin film on silicon 111 substrate. Then we pattern SRO and PGT by ICPRI as CH3 gas. And next we pattern the bottom electrode SRO and platinum and gamma alumina insulator by ICPRI in argon gas environment. And then the silicon nitride, that insulator actually we deposited by PECVD method at 300 degrees centigrade. And aluminum layer for interaction, we deposited electron beam evaporation. And another nice thing is we also deposited the photoresist. So you can ask why we need to deposit photoresist. Basically, if you go for application, then you need some impedance matching. So to before that, actually, we that's why for testing purpose we just use the photoresist for impedance matching. Then we created the diaphragm structure by general fluoride etching. Okay, so this is the details about the piezoelectric the thin film that we deposited over there. So we don't need to go through this one. So single element transducer, actually we just first fabricated and also designed and fabricated, but I will not go through that one. And the array transducer that we actually did here for our particular application here. So in the right side you can see the 8x8 channel the pMUT array, and the left side is the already packaged one PCB board. So it is like 100 micron diameter, the center region, and between 1 million to another element there's a pitch of 150 micron. So we did some kind of laser Doppler vibratometry, and it is like 1 to 10 megahertz, and peak voltage is 2 volt. And we found that in case of gamma alumina, the resonance frequency is 2.05, and in case of silicon dioxide is 2.200. So this is the resonance frequency we got. So this shows the laser Doppler vibratometry, and it is the rarefaction compression is showing, and the result is like that. So if you have the frequency versus displacement, it shows like the resonant frequency and also the mood shapes. And this is the experimental details that we did for ultrasonic wave transmitting and receiving experiment. And actually the channel 1 is just like your transmitter, and channel 2 is the receiver. So in one single channel we also did some experiment. So we found that it successfully just transmitted and received our signal. And this is also the another one, 1.4 megahertz one, and 1.53 another megahertz one. And finally we found that the transmission ultrasonic wave actually confirmed by our fabricated pMUT transducer. So this is also showing the another one with we investigated that within the 10 microsecond it can transmit it between the two channel 1 and channel 2, that is transmitted and received signal. So this is another the transmitter pulse that I am showing here. Just calculated that it is 3.12 megahertz. I'm going very quickly because time is not allowing anymore. So we also did some kind of sensitivity analysis with this fabricated device, and we just go quickly to our.
Could you please go to the conclusions?
Yeah, definitely. So we need to finish first. This is the output and of my voltage and sound pressure, just correlation between the two of the transducer. So now we just move on our conclusion that For your finite element simulation, you must include the anisotropy, otherwise your simulation will not give the correct results. And also the water you need to consider for your correct modeling purpose. So we found that with the laser Doppler vibratometry, we successfully successfully characterized the resonant frequency and also the mood shapes. And with the experimental findings, we found that our sensitivity of the device was 3.9 microvolt per kilopascal, and also with the polycrystalline, that is the ceramic part, was 1.3. So it is the huge significant improvement of our device. Finally, finite element simulation can be a great tool for your optimizing the pMUT device. Thank you for your attention.